Let's get started. Good afternoon, everyone. We have another CAN seminar, one of the last CAN seminars of the semester, probably, that we are really happy to have one of our students present today, and I'm especially feeling very good about it, of course, because of a project that myself and Professor Hasan Özer, we have been involved with on the project that Isam Gamya, the project's PhD student, main PhD student on this, has been working on with a lot of efforts, major efforts, and actually Isam is a very good student, just to let you know that he's, I know, very good friend of yours. But for 2 years he's been with me now as a PhD student and really doing great work. So, of course, that's the least we can expect from him. He has great results for us from the project, which is quite important in my opinion as an ICT project, because we're trying out new things as sustainable applications, especially on really soft ground, soft subgrades, how to rehabilitate and how to build construction platforms, as well as how to use some byproduct materials, quarry byproducts, as you see in the title, in different ways no one has tried before. And this is the second phase of quarry byproduct efforts for us in this project, that now we're finally putting things, we have put things in the field validation stage. So that's why it gives me more pleasure even just to have Isam to share with you the early results of this project. By the way, I should mention that the TRP, that's the technical review panel meeting for this project, is scheduled for next week. This is just intended as a seminar for general audience like us to learn about the project. More details, of course, we will discuss on the project findings next week on Friday. So with that, I would like to give the podium to Isam, who will share quite several slides with us today. So,
Thank you, Professor Tutuner, thanks for the nice introduction, and good afternoon, everyone. Is my voice good enough until the back of the room? Can you all hear me? Okay, I'll raise my voice. So today I will be talking about a project that most of you in this room are familiar with and actually have contributed to. I'm going to be talking about field performance evaluation of sustainable aggregate byproduct applications. As Professor just mentioned, this is a field evaluation of the uses of quarry byproducts in pavement applications. To start with, what are quarry byproducts? Quarry byproducts are byproducts that are produced at the quarry in different processes, such as the blasting, the crushing, and the screening of different techniques. These are usually very fine materials, passing number 4 sieve, smaller than 6 millimeter in size. And they're mainly sand materials, coarse to fine sand with some fractions of clay and silt. Just to give you a perspective about how important to utilize quarry byproducts are, if you see this big mountain of material, this is a huge mountain of quarry byproducts in just one quarry in the state of Illinois. And there's an estimate that the yearly excess production of quarry byproducts in Illinois is actually around 950,000 tons of material. So imagine these amounts of materials accumulating every year and interfering with the operations at the quarries. They have to pay for landfill, and it's an expense to them. And there's, of course, a big potential to incorporate these excess quarry byproducts in sustainable pavement applications, which is what we are investing in this project. To the start of the project, we have proposed some applications for these quarry byproducts to be used in pavement construction, such as subgrade materials, subgrade improvements, base materials, sub-base materials, and even in hot mix asphalt. So the main applications that we came out with for quarry byproducts in unbound layers and stabilized base and sub-base layers are to use the QB to fill the voids and gaps of large stones as aggregate subgrade on soft subgrade materials. That was one of the applications. Another application was to blend those quarry byproduct materials with other coarse aggregate materials, recycled materials such as fractionated wrap and recycled concrete aggregate with other additives like cement or fly ash on stabilized base materials. We are also investigating to reduce the amounts of quarry byproducts that are produced in the future by giving more flexibility to the standards and see if we can actually increase the percentage of fines that are permitted in the current base materials that are being used at the states. So going up to 15% fines instead of the current standard, which allows the maximum of 12% of fines only. Also using quarry byproduct as a stabilized material with cement or fly ash as a base material, or as a sub-base material in inverted pavements with regular base course material on top. So in order to investigate those applications that we had in mind, we actually planned and built some test sections, real size test sections. And so for different applications, we've built those test sections at different subgrade levels that we've engineered, as I will explain now. So the first set of applications, we were thinking about construction platforms, which are the platforms that are being used by the construction equipment in the sites, not the traffic, but the construction equipment before the road is built. And these are usually built on really soft subgrade soils, typically CBR1 soil, which is basically a swamp. It's very wet, very soft soil. And for our applications with construction platforms, we had 4 different applications that we were investigating. And we are built 4 different test sections. So the first application was to mix quarry byproducts with large rocks. We call them CSO2 for now, and I'll explain those later. And build them in 2 lifts or in 1 lift. So these are the same, but 21 inches of material built in 1 single 21-inch lift, or in 2 10.5 inches lifts. And then other applications are the 15% plastic fines CA6 material and 15% non-plastic fines CA6 materials. And those will be constructed on weak subgrade of CBR1, which will be tilled and engineered in the field. Just to explain what's the CA6 material and the CSO2 material I'm talking about. So the CSO2 material are, these are the gradations of these materials. So the CSO2 is a really open-graded large rocks up to 6 inches in size rocks with very little amount passing the 2 inches, so they're huge rocks. And there's a big voids in between that can be filled with quarry byproducts for stability. CS6 is the regular base material that are used in the state of Illinois, just like this. And it has a percentage passing number 200 of the maximum permitted is 12%, usually from 8 plus minus 4%. And the quarry byproducts are just the sand-sized particles, the small sand-sized particles. And as I was mentioning, that we were going to be building 24 inches of these material on top of the subgrade, and that's because of the specs in Illinois now from the subgrade stability manual for a weak subgrade of CBR1 that requires a backfill cover requirement of 24 inches of granular material almost on top if the CBR is weak. Other applications that we have for the quarry byproducts are using the same materials that will be used in the construction platforms, but this time top them with 4 inches of HMA and use them as low volume road applications. So we have the 21 inches of the materials, we have a capping layer, and then we have 4 inches of HMA surface on top. And these will also be built on a very weak subgrade of CBR1. More applications, proposed applications for quarry byproducts that have been built in the field are mixing those quarry byproducts with recycled materials, the fractionated wrap and fractionated concrete, and stabilizing them with a stabilizing agent such as cement or fly ash. So we also built 4 test sections. In one test section, we have quarry byproducts mixed with wrap, 70% by weight of quarry byproduct, 30% wrap, and 3% cement of the total weight of the quarry byproduct and the wrap. The same thing, but changing the wrap with fractionated concrete, and the same thing, but using quarry byproduct, wrap, and fly ash, 10% fly ash by weight of the quarry byproduct and the wrap. And then we had one test section that has a cement stabilized quarry byproduct, just the quarry byproduct itself, with 3% cement by weight. And those are low volume roads applications, so they are 12-inch base material topped with 4 inches of HMA surface. One thing that I forgot to mention here, and I need you to mention it because I will be showing the results. So in each section, the sections start from left to right. They're numbered 1, 2, 3, 4. So section 1 is the leftmost section, number 4 is the rightmost section. And in each section, we have 2 points. So in section 1, we have point 1, 2. Section 2, we have points 3 and 4, and so on, that we are measuring the properties and basically doing the QA, QC, and the RUT measurements at these points for later on. Coming back to the applications, other applications that we had in mind is to investigate the effect of the type of the quarry byproduct. So we're also building another cement stabilized quarry byproduct section, which has a different type of quarry byproduct, the same amount of cement, 3% cement by weight. We also have 2 test sections that are inverted pavements. So we have the stabilized quarry byproduct mixed with cement or fly ash in 2 separate sections. And they are topped with regular base material, so 6 inches of the stabilized quarry byproduct and 6 inches of the base material, and topped with 4 inches of HMA surface. And these test sections will be built on a CBR 6 material, which is the minimum CBR, which doesn't require any modifications of the subgrade or building a subgrade modification layer in the state of Illinois. So in total, this is a plan view or top view of the constructed test sections as they were constructed in the field. So we have 4 different cells here. We have cell 1. The north side is the HMA paved sections. The south side is the construction platforms. Cell 2 and cell 3 have the stabilized quarry byproduct sections. Cell 1 is built on a CBR1 very soft subgrade, and cells 2 and 3 are built on a CBR6 subgrade. And of course, if we have good pavements, or if we are constructing good pavements, we need good drainage. So we had to design also some drainage layers in transverse drainage and longitudinal drainage layers to drain all the water from the layers in the field. So now after that, we have those applications for the quarry byproducts. We've moved to the construction phase of this project, which took us some time to engineer the subgrade and do all the construction activities. So the basic first step of each construction is doing the earthwork, so the excavations. And in some cases, because this project has been built on an older project, we had some areas where the previous base course materials was deeper than our intended excavation depth. So we had to clean those and bring some backfill materials or borrow material, and then engineer the subgrades or level the subgrade to our elevations. And the second step was doing the drainage layers. So we had the perforated pipes, and we had the CS7 gradation, open graded drainage aggregates just underneath the subgrade level to start with. Now, the major step before we build the test sections was to engineer the subgrade to the required CBR values that I was mentioning. The CBR1 very soft subgrade for the subgrade improvement applications, and the CBR6 for the base course and subbase applications. So in order to engineer the subgrade, our subgrade soil here at Atrial is a low plasticity silt and clay salt. According to the Unified Soil Classification System, it has a PI of 6. And we already have established moisture content and CBR relations. So we know that at a certain moisture content of this soil, it corresponds to a certain CBR value. For example, a CBR6 is at a moisture content of 12%. CBR1 is a moisture content of 15%. So we need to target those moisture contents in the field in order to be able to get the CBR values that we're engineering. And also we have some established DCP, which is the dynamic cone penetrometer, and CBR correlations by some empirical equations that correlate the penetration rate of the DCP to the CBR. And we were using these to investigate the CBR profiles that we're getting at different points. Just a brief explanation of the subgrade preparation procedure. So we start with initial wetting of the subgrade if we need it to go below what we have right now. And then we till the top 14 inches of the subgrade with a tiller to make sure that the water is uniformly mixed and that we get a uniform subgrade profile across the depth of the soil. We don't get like a weak CBR on top and then a regular CBR on the bottom. So we had to do that. And then we had to collect the samples to estimate the moisture content. And we were using the microwave method because we had to do it fast for the construction to proceed fast. Then the subgrade was rolled or compacted with a sheep's foot roller, which works ideally better for clayey soil or silty soil. And then we get the CBR profile at the different measuring points that I mentioned before, the 8 points, the 2 points in each section. And we look at those profiles. So if they are satisfactory, we seal the surface with a tack coat, and the subgrade is ready to build the construction materials on top of it. If it's unsatisfactory, we go through iterations. So we do a moisture adjustment, and we repeat all the steps. So we till this subgrade again, we add the needed amount of water. If it's too dry, we have to wet it. If it's too wet, we have to dry it, and compact it again, get the DCP profile again, and so on. Just showing some quick pictures. This is a tiller tilling the subgrade, compactor compacting the subgrade, and then after that, these are the marks that we get with the sheep's foot roller. And then we get the DCP profile, for example, and we're shooting for a consistent profile across the depth of the soil, just like these points. So these are the 8 points that we have, and it should be consistent. That's for a CBR6 subgrade, and that's actually the DCP that we drop at the different locations to get those DCP profiles. And then the wetting of the soil, we calculate the amount of water to add if we need to change that and go through different iterations. This is the sealing of the subgrade after it's ready. That's the CBR1 subgrade, and that's the CBR6 subgrade. In the case of the CBR6, we did also a smooth rolling. We rolled it with a smooth drum roller to level it basically on the surface before putting the material on top. That was not possible with the CBR1 because it's basically a swamp and it's very difficult to do that. And also for CBR6, we were able also to do some LWD, lightweight deflectometer measurements, to estimate the modulus of the subgrade. Now I will show some results from different trials for the subgrade engineering and preparation. And what I'm showing here is the distance from the beginning of the cell. So that's the longitudinal distance here. These points, the 8 points here, are the points of the measurements that we had. And we were basically monitoring from trial to trial, and each trial is a trial of moisture adjustment or tilling and repeating the DCP and getting the profiles. So if you see, we start with something very random. The soil is, the CBR is everywhere, and with continuing the trials, we get something that is more consistent. This red line here is the final trial. So our target CBR is 1, and we were able to get a CBR of less than 1 at all the points. That was the section for the construction platform. And each point here is a CBR profile for 12-inch depth, the average CBR profile for 12-inch depth. But we made sure that this average is also consistent across the depth. This is the same results for the HMA paved cell 1 north, also showing a consistent CBR of less than 1 on all the different points. For the CBR6 materials, cell 2, we had only to do 2 trials, fortunately, for that one. And we were also getting around our target CBR. Similar thing for cell 3. And this target CBR was 6, and we were getting CBRs from 5 to 8 almost, but they were all around 6. So that was the first step, so that we have a controlled subgrade to build the applications on top of it, so that we can compare one-to-one performance of the applications if everything is kept constant. So now I will move to the construction of the cell 1 layers that I was explaining, those applications. And those applications for QB are unbound applications. They're not stabilized. Those sections, the construction platform and the HMA paved sections, were built together because they're pretty much the same, except that the north sections were topped with 4 inches HMA at a later stage. So as I was mentioning, that I will mainly talk about the construction of these 2 sections, the QB with the CSO2 in 2 lifts and in 1 lift, because they were a little bit more challenging than the other 2 sections. The other 2 sections is just placing the material, compacting it after doing some moisture adjustment. But these ones were a little bit challenging. And what's challenging is that we have the large rocks, and we're trying to fill it with quarry byproducts. So we need to know the amount of quarry byproducts that we can use or we're able to use. We need to find a technique of mixing those 2 materials together. And in order to do that, we investigated this in the lab first. So we built a large box, 24 inches by 24 inches by 21 inches, with one of its faces having a clear plexiglass front, so that we can take images and actually control or monitor the percolation of the QB inside the large rocks. And just as a last image, this is the box filled with the large rocks. And the way we were doing this is that we were filling the large rocks first, putting the QB on the surface, and then using a vibratory roller, lap-size vibratory roller to use the vibrations to percolate the quarry byproducts inside the large rocks. And we were trying different, basically changing different parameters. So we were doing 1 lift and 2 lifts compaction of the quarry byproducts. We were also monitoring the effect of water content of the quarry byproducts, the effect of how much we can put at different water contents. We were varying the amount of quarry byproducts between 20% by the weight of the large rock to 40% by the weight of the large rock. And we were also changing the support condition from using a rigid steel support condition or using the subgrade material that we were using in the field, and seeing the differences in the results. So what we found out basically from this study, and I will show you some videos now of the application of the quarry byproducts in the lab. So that's basically how we were applying them to the surface at different percentages. And then once we have the quarry byproducts sitting on the surface, we were using a vibratory roller to compact those quarry byproducts. And you can see the percolation and compaction of the quarry byproducts in the field. In between the large rocks. So the main things that we got out of this study was that the optimum amount of quarry byproducts that we were able to pack in case of dry quarry byproducts was around 35% by the weight of the large aggregate, while in the case of wet quarry byproducts, at the amount of the moisture content, existing moisture content of the piles as they were received from the quarry was around 25%, and that moisture content was around 2.7 to 2.8%. We also didn't see much differences between building the quarry byproducts in 1 lift, so filling the whole box and then putting the quarry byproducts on the top, or in 2 lifts just like this, like 1 lift with quarry byproducts on the surface and then another lift on the top. So after we had this study and we found that 25% is optimum, we moved to the field and we were trying to replicate the exact same procedure. So we put the large rocks first, and then we put the quarry byproducts on the top, spread them with a skid steer, and then we tried to compact them. But what we got in the field was different from what we got in the lab. What we got in the field is that the quarry byproducts on the surface were compacted into a relatively thick layer on the top, which inhibited any additional quarry byproducts from actually going down inside the large rocks. So that was building the first lift of the 2-lift application, and we had to fix the situation somehow. So what we did to fix this situation is that we used the bucket of an excavator to basically mix and shovel the materials together. And then we were brainstorming to find a way to do that, like why did it work in the lab and why didn't it work in the field. And basically the difference between the lab and the field is that in the lab we had more of a vibratory action. In the field it was more of a compacting action. So with compaction we were compacting the byproducts on the top. And what we actually need, we need a more slow and uniform application of those quarry byproducts on the surface, and more of a vibration effect in order to successfully percolate those quarry byproducts inside the large rocks. And in order to do that, we had actually in the lab to shovel those quarry byproducts manually inside the large rocks. So we were using shovels. We were a team of 4 PhD students, 2 professors, and postdocs even, just shoveling on the hottest day that summer quarry byproducts inside the large rocks. And the amount that we shoveled is actually 16 tons of quarry byproducts inside those large rocks. And it was working successfully this time because the application was slower, so we were manually shoveling it and then using a vibration, stronger vibration to do it, and it was giving us similar results to what we had in the lab. And of course, we were doing it this way manually in the field in this experiment, but in the field, like for the future applications, the way this should be done is to spread the quarry byproducts more uniformly from like those salt trucks, or using spreaders where we spread the quarry byproducts from those spreaders, and then we have a big vibrator roller following it and shaking those quarry byproducts inside. And in the field, what we were able to pack as a maximum amount for the 2 lifts was the full 25% quarry byproduct by the weight of the CSO2, which we found in the lab. While in the 1 lift, we were able only to pack 16.7% by weight of the CSO2, mainly because 2 reasons for this. The first reason is the moisture content of the quarry byproducts in the field was a little bit higher than what we were experimenting in the lab. So we had around 3.2 or 3.2% moisture content in these quarry byproducts. The second reason is the boundary effect. Because the box is smaller, you can pack more of those quarry byproducts around the corners. But in the field, because you have more of your aggregates in the middle and you don't have as much boundaries, so we found out that the boundaries can actually accommodate more of the quarry byproducts than the center of the sections. So we were able to pack less quarry byproducts in 2 lifts. So basically, that was the construction of the unstabilized sections. Now I will move and talk quickly about the construction of the stabilized layers. And it was pretty much the exact same procedure for all the stabilized layers. The only thing that was changing is the stabilizing agent or the materials that was stabilized. And I'm not going to read this, but I'm going to show you some pictures and explain the procedure quickly. So basically, we have the stockpiles outside, and we were sampling those stockpiles from different locations, creating one big stockpile, then mixing that stockpile together from the bucket of a backhoe, and after that, collecting some moisture cups to estimate the moisture content, and some buckets to estimate the loose weight of the material. So we have the loose weight of the material. We can calculate the density. We know the amount being put here because we know the volume of the bucket load. And if we know that, we can add the cement or the fly ash quantity by the weight of the material. So first, mixing the material, taking the moisture cups or the moisture of the material, then adding the cement with the current moisture and mixing it again, which we can call dry mixing or mixing below the optimum moisture content. Then adding more water and the amount of water that was added to get into the optimum moisture content, and then mixing again, moving on a truck and hauling it to the site where it will be built. Just showing you here some of the materials and the final look of the material after they've been mixed together. So this is the frap section. You can see it here. This is the one with the concrete. This is the one with the frap and fly ash. And then these two are the cement sections. Now, the placement of the material is also a bit challenging because everything has to be done fast before the cement or the fly ash sets. So we had to put the material, spread it with a skid steer, till it again on site, and build it on site, and then rolling it. And we were doing that in layers, in 2 different lifts, 6 inches lifts each. And we were intentionally putting more material than needed so that we can shave the top of the material and then roll it again instead of running out of material before the cement sets. And basically, we had very good quality control from the contractor, so we were able to get the exact layer thicknesses, or as accurate as possible layer thicknesses to the 12 inches or the 6 inches that we were shooting for in the construction. After that, we had some QA, QC measures on all of the built layers. So we had density measurements. We were using the GeoGauge and the LWD to get the layer moduli of the materials. And I will share with you some results of the lightweight deflectometer back calculated modulus for the unbound layers, starting with the construction platform layers. These are the CSO2 with a QP in 1 lift and in 2 lifts, the modulus on top of the material, and then on top of the capping layer, which was added later. And these are the plastic fines and non-plastic fines sections built in 3 different lifts and then capped with the material. One thing to notice here is that in most of the sections, the final modulus was around the same, like around 200 megapascal plus minus some variations. The same thing for the low volume roads, except that in the 2 lifts one, we had a slightly lower modulus, but eventually they were in the same range almost for all the different sections. For the stabilized sections, we were monitoring the curing or the change in modulus with the curing time. So we were doing the LWD at different times, starting from few hours after the construction and then several days after the construction. And we were getting really good values of the modulus of these materials. The best performing in terms of modulus, of course, was the FRAP with the QB with the cement, and then followed by the QB with the fractionated concrete and cement. The sections with fly ash had relatively lower final modulus values compared to the ones with the cement. And even they were lower than just the cement with the QB by itself, even though those fly ash sections had some RAP mixed with the QB in them. This is also comparing the inverted pavements layer modulus that we were getting. So in the first few drops with the LWD, the first few hours or days, we were doing the drops on top of just the inverted pavement, the 6-inch stabilized layer. And then after that, we were topping it with the regular base course material, base material on the top. And then we were doing the drops on the top of the base material. So you see also the modulus increase with time. For the cement and the fly ash, and the cement was also outperforming the fly ash by much. But the fly ash and the control section, which is just regular base material, were pretty much the same in terms of modulus. The last step was, of course, the HMA paving. So we had 4 inches of HMA put on top of the pavement, and we were doing also the sampling in the field, in the plant, the coring to get the layer, the thicknesses of the cores, as well as the density checks and the monitoring of the temperature and some laboratory investigations of the properties of the asphalt that we were using. Other than those, we have some other construction activities that I will briefly mention. We had some pressure cells installed in the sections, cells 2 and cell 3, which had a CBR of 6 in some of the sections. And Professor Al-Qadi actually helped with the installation of these pressure cells, as well as many of the students in here. And we also have some thermocouples installed in those sections to monitor the temperature of the sections, the HMA layer, the unbound materials, and the subgrade. And basically, it's more intended toward the winter to see how much freeze-thaw cycles we might be getting, as well as monitor the temperature of the layers that we have. And we've installed these only in cell 1 with the large rocks and the plastic and non-plastic fines. And we have like 4 different thermocouples in each section at different depths. Now, after the sections were constructed, we've actually started running some accelerated pavement testing on those sections. So for that, we're using the Atlas machine that we have in the lab. The accelerated transportation loading assembly, which has one of the largest spans in the world, 85-foot loading length with 65-foot constant velocity loading. It's capable of applying loads up to 80 kips, and we can change the lateral wander up to 3 feet laterally, and can go up to 10 miles per hour speed. And that's basically a plan view of Atlas and its size. So we started the performance monitoring of cell 1 with the performance monitoring of the construction platform sections that we've built. And I have a small video showing Atlas running. I don't know why it's flipped upside down here. Just flipped now. The wheel isn't that wide, but used to run fine on my computer. So the tire that we're using is a super single wide base tire. We have a constant unidirectional load of 10 kip, tire pressure of 110 psi, constant speed of 5 miles per hour, and we're using a modified dipstick to measure the rut at different passes. So we basically start with a 0 pass, we measure the rut, or before we started the experiment, then 1 pass, 10 pass, 100 on a logarithmic scale, and we were able to get up to 20,000 passes on these sections. Our failure criteria was a 3-inch or 76 millimeters of rutting, and the average values of all sections, we didn't fail any section. We only failed 1 point in the section with the non-plastic fine, as I will explain later. So here I'm just showing briefly some of the results from section 1 and section 2, which are the primary crusher run, constructed in 2 lifts and constructed in 1 lift, the large rock with the quarry byproducts. And you can see the rutting values up to 20,000 cycles in here. And these are the dipstick measurements, and then later on we convert them and we get the actual rutting compared from the 0 point up to the maximum. So if you see those sections, the best performer was actually section 4, which is the 15% non-plastic fines. We had less than 15 millimeter of rutting at 20,000 cycles. The worst performer by far was the non-plastic section, which accumulated almost 70 millimeters, a little bit less, maybe 68 millimeters of rutting at the end of 20,000 passes. But 20,000 passes for construction platforms is a lot. So most sections, I would say, have performed well in this case. And if you look particularly at this point here, where you have the increase in slope, this is where we got a lot of rain while we were testing, and Atlas was running at that point. So in these points here, between 10,000 and 10,500, there was a little bit of rain, and these points here, but the machine was stopping, so there were no loading of the pavement. But in these points here, we had loading of the pavement plus rain, and that accelerated the accumulation of rutting in those pavements. The second thing was the asphalt sections, which were the same but with asphalt on the top. We also had done the accelerated pavement testing on those sections. As you can see here, and measured the rut. But in this case, instead of using the dipstick, we were using laser profiler, so it can actually give better resolution. We can collect more data points and measure the rut. So in the case of construction platforms, our failure criteria was 76 millimeters, or 3 inches. In the case of asphalt, our failure criteria was half an inch, or 12.5 millimeters. We were applying the exact same wheel, the exact same loads, and everything. And we were actually able to get up to 90,000 passes as of yesterday. So I only have the results here up to 75,000 passes, but we were able to get up to 90,000 passes with those sections. And I'm also showing here the results of rut accumulation at different passes, from 0 pass to 75,000 passes for different points in one section. That's section 1 at 2 measuring points, and then section 2. And then these are the average results for the sections up to 75,000 passes. So the failure criteria is 12.5 inches, and the maximum rutting that we got at 75,000 passes was actually 7.5 millimeters. So it's way less than our failure criteria, and we didn't fail the section. We were actually hoping that with the cold weather that we had, and with the larger number of passes, that we can see maybe another failure criteria, such as fatigue cracking starting to form. But up to 75,000 passes, we didn't have any cracks in the section. Again, here, the worst performer up to 75,000 passes was the non-plastic fines, which was performing better than the section with the QB and the large rock built in 2 lifts earlier, but then it outpassed it later on. And the best performer section was section 2, which is the QB built with the large rocks in 1 lift. And then the second best is the non-plastic fines that was performing the best in the construction platforms. But overall, like relatively speaking, all these sections performed pretty much the same, and they performed well. So things are working. This is the exact same plot, but I'm showing here the number of passes on a logarithmic scale. Maybe it's more convenient for others to see the trend on a logarithmic scale. And with that, I actually end my presentation. I would like to thank all of you for attending. I would like to thank all of you for actually helping and contributing to this project. I've got a lot of help from my research group, from Professor Al-Qadi's research group, from the research engineers here, and from everyone. So thanks for your help and for attending. That's it.
I don't know how he does it, but he does usually show 60 plus slides, and he's below, he's under 45 minutes. 40 minutes. He went under 40 minutes now. So questions?
I have a couple of questions. First of all, thank you so much for your presentation. And it shows you did a lot of good work, huge work. And I also did PhD field work. I know how hard it is. And good thing you are getting huge amount of rich data. There's the very sellable Just one thing first. I saw when you measure your wrap, paved section, your wrap performance for the section 4 is different than when you measured on the without paving. Can you go back to your rut depth slides? Yeah, this one, and look at the without paving.
You mean the trend is not the same?
Yeah. So, yeah, section 4.
Yes.
Here is the best, but in the second case, it was the performing.
Yes, so in the case of the construction platforms, the best performing section was section 4, and the second best performing was section 2. In the paved sections, the trend was like these two were quite similar to each other, but actually section 2 was performing a little bit better than section 4 in this case. And the reason is not fully known now, but it could be the thicknesses of the asphalt, because the thickness of asphalt might have varied a little bit between these two sections, so that might have contributed to one section rotting less than the other. That's one thing. It could be also just construction variation or construction quality of those sections. Maybe the measuring points, you had some variations between section to section. But overall, if you look at these numbers, like the numbers themselves between 5.5 millimeters and 6.2 millimeters, the difference isn't that big.
What is the composition again between section 2 and section 4?
So in these sections, you have 21 inches of material, the material that we are investigating on top of the CBR1 subgrade, topped with 3 inches of capping material, which is a dense graded base material, and then topped with 4 inches of HMA on the surface.
So for the QB product, QB plus cement on what?
No, this has no
Without-
cement.
okay.
Yeah, these are the unbound applications.
Just QB?
Yes. Which section are you talking about? Because
Section 4.
Section 4 is 15% non-plastic fines. So in this section, it's a regular base course material, but instead of the like specs in Illinois now permits you to put up to 12% fines only, and that's the maximum amount of fines that you can have in your CS6 material. And we're trying to get 15% fines instead of 12% fines. So if you get higher fines and if you can show that it performs well, then eventually you end up producing less quarry byproducts in the future, because you can permit higher fines in your material that you ship to build construct roads with.
Yeah, my query was just why we, I think you answered that, I think because of construction variability in the HMA there, so you are seeing different. Also, I think if you run statistics, you will not see that
Right, so these are-
significant difference between these variations. Second thing is, so your control is then just the regular fines.
So for
When you
this,
compare the QB
for these sections, actually, there is no control, but the control is, so we have two sections here. So we have, for example, the QB, the CSO2 built in 1 lift and 2 lift, and we have the control in a previous study where these were built without the QB, just the regular CSO2 material before. So we're comparing these to the previous study results, and we have found out that these are performing way better than those before. Same thickness, same subgrade conditions, same everything, even the same capping material and the same sources of the materials. So the CSO2 material and the capping material are from the exact same source. So everything is the same.
Are you thinking to do like cost analysis on those things?
Do what exactly?
Life cycle cost analysis.
Definitely, yeah, that's coming, modeling, life cycle cost analysis. Bear in mind also that these results are just preliminary results. Like I'm showing results for asphalt, I'm showing them at the temperatures that they were measured. Everything will be normalized to like the temperatures in the summer, and you will get like different results. We can also curve fit these into permanent deformation models like AN to the B sorts of models, or we have our own model for permanent deformation that we can fit them into. So these are just preliminary results. This study has basically the construction started at the end of July, so everything you've seen today is only 4 months old. So more things are coming hopefully in the future.
Okay, thank you.
Thanks. Any more questions?
I have a question. So I have a question about the size. How did you select the size of the cells? And how did you make sure that no one, like the cell, for example, 2 is not affecting the result in 1 or 3 and 2.
Yeah, so basically the sizes of the cells is, if I go back to Atlas, so Atlas has a wheel span of 85 foot, and we have a 65 foot of region where we can achieve constant speed. So we need to make sure that we're also measuring at a constant speed of 5 miles per hour. So we have actually 65 foot of section here in the middle where we can be consistently measuring at a constant speed. And then we have places for the crawlers where the crawlers of the Atlas are sitting. The spans of the sections are controlled by the limitations that we have here. So the sections on the side are a little bit larger because some areas here are for the crawler, and then some areas here are transition zones where the wheel is gaining speed before it goes up to the 5 miles per hour in the middle. And each 2 sections here, so you have the crawler area, you have the transition zone, then you have the actual section, and then you have another section, and then you have another transition zone here in the middle to reduce the effect of sections, like different, as you were saying, different sections contributing to other sections. And the same thing on the other side. And just to answer your question, if you make sure that one section is affecting the other or not, there might be some effects, but those effects, in my opinion at least, are not very large. And the reason I'm saying that is because in one section, at 2 measuring points that are 5 foot apart from each other, you can still see differences. So you can see in the same section, see differences. And definitely if you see differences in the same section, then you're seeing differences in different sections.
Thank you.
Mohammed, any question?
A nice presentation, by the way. The question is, normally when we do 2 lifts, we were expecting higher quality control and hence better performance. But your primary results show, preliminary results show the opposite, that 1 lift is always better than having 2 lifts. And from sustainability point of view, usually we use the lower lift to have more byproducts or sustainable products where we can dump them there and have better quality in the top left. So is there an explanation?
There's no exact explanation for that, but we have a theory about it. If you look at these pictures here, we think that when the first lift was constructed, after I was telling that it didn't work and we had to fix it and use shovel the material basically together with the excavator. So what might have happened, and this is just still a maybe explanation, is that we ended up getting a lot of quarry byproducts left on the surface between the 2 lifts. So those quarry byproducts are actually reducing the direct contact between the large rocks together. So they're reducing the shear strength of those layers, and they're acting like let's say a weak shear membrane or a failure shear, what do you call it? Like a weak layer in between the 2 layers that is causing more permanent deformation, because permanent deformation is closely related to shear properties of unbound materials. So you don't have maybe the direct contact between the large rocks, which is giving the high shear strength of those materials when you have the quarry byproduct as a layer in between those 2 layers. So that might be an explanation, but later on when we do the trenching, we can know for sure what's going on. Another thing that I would point out, even though that this might be the explanation, if you look at the rutting results, so this is the point-by-point measurement from section 1. So in section 1, as I was saying, in each section we have 2 points, and section 2 we have another 2 points. So if you just follow the numbers here, you see that section 2, which has the 1 lift, a QB, the results were more consistent, while in section 1 you see that 1 point was varying more than the other. So it might also be just because of local variation in the material, construction quality, construction variation sort of differences.
Yeah, although we packed less, 17% in the 1 lift, I think the uniformity of the construction was better achieved than our first trials with the 2 lift section. I think that's also, there's also some aspect.
So in field application, are you going to use only 1 lift always?
From what we have seen, that worked very well in the field and actually is doable. Yeah, 1 lift you can actually achieve even 16-17% QB filling the voids, and that's possible. That's 21-inch construction. The other one is 11 or 10 and a half and 10 and a half inch 2 lifts. So
have this large amount or large thickness of a layer, how is the compaction effort going to be working well on that?
Well, I guess if he shifts all the way to the two rutting profile pictures in the end, one way to look at them is the slopes. Look, right, for example, here, this is for construction platform. If you look at how the slopes are changing, those are the two middle curves, right? The top one is, what, the two lift?
That's the one left, and then this.
Yeah, well, sorry. The second from the top is actually the top of the QB ones. So how the slopes are looking and things, if you think about that, the one left one is, let's see, section 2, that's the second from the bottom, right?
Yes.
So, but what happens in the rainy day also, the slopes are going a little higher there, and then slopes are stabilizing, the accumulation slopes. So it's hard to tell again, but nevertheless, overall, the rut depth is more uniform and more shaken down, less accumulation of rutting. And actually, that's probably easier to see if you move to the HMA sections. And there's immediate primary type rutting right away, right, in the asphalt. Okay, so then if you look at what's going on with the increased number of passes, if you look the QB with CSO2, the one lift and the two lift, that again, the circle and the X, right? They're pretty much following the same kind of trend, both. Whereas if you look at section 3, which is the worst with plastic fines, after about 3 millimeter, it just goes very high. The slope is very high, and even the slope of the 15% non-plastic fines is high compared to the QB section. So QB is really performing in a low to medium volume road with 4 inches of HMA, better than, I guess, even the CA6 of 21 and 24 inches in this case.
So I had a question there. What's the type of QB here? Is it type of QB product here?
It's limestone, basically. I think, I don't remember the numbers correctly, but 70-something% CaO. We did the X-ray, XRF, X-ray, what is it, fluorescence on these materials.
So if it was something different, are you going to expect the same trends for one lift and two lift?
In what sense?
That QB is, for example, dolomite, not limestone, or
Oh, dolomite and limestone, they're basically the same. They're all our carbonatic
nice.
rocks that we have in Illinois, sedimentary carbonatic rocks. So I don't think there's going to be any much difference. We actually tested, 4 different quarry sites in the previous project, found little differences in overall from primary, secondary, tertiary crusher. Right. I have one question. You're showing the curing effect of some cement stabilized sections in one of your plots, and then right that one. No, the next one. Right there. You say placement of CA6. What day is that?
Probably 9,
Right day.
8 or 9. I think it was 8, day 8.
And then a rapid increase in modulus behavior. So, do you have some explanations on what's going on right after placement of CA6?
Could be the water, because like this is day 8 and then this is day 11. So at the placement, the CA6 was compacted at the optimal moisture content. So at the surface when we're doing, because you know when you're rolling the material, some water will just maybe like come to the surface. So the surface is a little bit wetter or something. So at the first day or the first time you run the LWD, maybe you have more moisture on the surface that is leading to a lower modulus, but if you leave that layer to settle down under the sun, you dry out some of the material, maybe the modulus increases. And then also the cement is curing, definitely. But yeah, that's a big increase, big jump.
For cement curing, is CA6 bringing some more moisture into the cement layer for additional curing, a rapid increase?
That could be also a case, not exactly sure. But those results are actually the average of 4 points, 4 measurements, and the standard deviation isn't very high. So they are consistently giving this trend. So it's actual, like it's true. It's a true trend. But what's the main cause or what's the main thing behind it? I'm not really sure.
When the last was
Yes,
collected, then right after that we had the HMA place, right?
Right, maybe a week after.
Oh, still another week?
Yeah,
after?
because if you remember, we had to ship the LWD and then the HMA was delayed.
I have just one more question. So now you tested like the sections and they are performing like now they are really performing well. But I have a question, like after a cycle of freeze and thaw, like during the spring, are you planning to like check how?
This will be actually more critical with the stabilized sections, which we haven't tested yet. But at least those are cells 2 and 3, which we'll be testing next summer. But at least we have our thermocouples to see how many freeze and thaw cycles we're gonna have before summer, before we test them. Because I remember from the course I took the soils, not soil, transportation soils, we were talking about the effect of freeze thaw on the performance of stabilized layers, and it really weakens them. Like cycle after cycle after cycle, you see a big jump in the strength and in performance of those stabilized layers. With the unstabilized ones, I don't think the effect will be very high, especially for the open graded ones, like the large blocks with the QB. Those ones, I don't think they are really high moisture susceptible. Like you don't get the capillary action of the water coming inside those layers really easily. So I don't think they will be highly affected by freeze thaw compared to the stabilized layers.
It's like you lose 10 psi with every cycle or so. The stabilized material loses strength in time with the freeze thaw cycles.
Yes.
I think you also ran FWD on the.
Yeah, we ran FWD
HMA
on top of the
surface.
HMA surface before we tested, and then we will run them again after the testing, hopefully after next
Now we
week.
will
Yes.
compare to the FWD.
We will compare FWD to LWD, right? And then we have the GPR also. I haven't presented everything that we've done, but we also have some GPR results that will tell us probably which layers are rotting more and which layers are contributing to the rotting that we're seeing here.
Are you going to bring those into the TRP? slides?
Not for this week, no. These are not analyzed yet because we haven't done the before and after. So we've measured the GPR profile before, but then we need to do the after, which has to be done after the testing, and we just finished the testing yesterday. So
Do you have the FWD results also?
the after the results I have.
Maybe a good thing to include those too.
Yep. One question.
Anything else? Question, comment? Well, stay tuned. There's more to come for this project, but thanks, Issam.
Thank you.